All right, Precal B. We are going to be taking a look specifically more into the rational function idea now. We had a little offshoot there where we talked about reciprocal functions, and in a way that seems like it should be simpler, but actually we looked at reciprocal functions involving a variety of things. When we look at rational functions are generally going to be used to describe a category of functions where it is polynomial over top of polynomial. Some reciprocal functions will kind of have that definition too if the polynomial on top is 1. Or even a constant, you could just say it's a stretch on some sort of reciprocal function. But we had looked at ones that involved even trig functions and exponential functions and the like, and so we will not be doing that now, which is great. So we'll be focusing on rational functions where, as it says on this screen down there, it is going to be a rational ratio. So that's where that comes from, is ratio of two polynomial functions. So if you said that the rational function r of x is defined as polynomial p of x divided by polynomial q of x, then that would be an appropriate way to define how we are going to treat rational functions. Let's just dive right in. That's basically all we need to know in terms of terminology, which is great. All the rest of it should be things that we feel comfortable with. So this actually, funny enough, is basically a reciprocal function, but that's okay. I'm going to follow along more with what the textbook is doing in Chapter 9 because, I have a textbook that does this now, as opposed to freelancing a little more during the limit section. So we have y. Oh yeah, highlighter. All right, we have y is equal to 10 divided by x. All right, so I'm going to use a table of values first. So here we go. Table of values. So we're going to have x against 10 divided by x. So I'm going to just, I don't know, if I were to default without knowing anything, I usually go something like this for my table of values. I like to do things tight to the origin. Because a lot of times that's where some interesting stuff happens for a lot of the functions that we look at. So I want to make sure I don't miss anything around there. If I end up like this doesn't give me a very good description and I have to go out further, then that's fine too. But just as some random values here, let's go. So 10 divided by negative 2 is negative 5. 10 divided by negative 1 is negative 10. 10 divided by 0, All right, we'll come back to that in a moment. 10 divided by 1 is 10. 10 divided by 2 is 5, and then I could probably pick out, if I wanted to extend this a little bit more, 5 would be a nice value because 10 divided by 5 would give me 2, and I could even go like 10, and 10 divided by 10 would be 1, and that would give me a little more of an idea of how this would look graphically from those pieces of information. So I mean, if I'm going to do this by hand, something like this. And so negative 2, we'll say that that's negative 2. I'll go by 2's here. Negative 2, negative 5. So I'm actually going to say going up this way. Yeah, I guess I'll do the same thing. 2, 4, 6, 8, 10. And negative 2, negative 4, negative 6, negative 8, negative 10. All right, so at negative 2, I'm down at negative 5, which is about halfway. So I'm about right there. At negative 1, I'm at negative 10, which is down here. And then at 0, okay, we'll try to figure out a little bit more about what's going on there. But at 1, I'm at 10. And then at 1, that's halfway. My apologies. 1, I'm at 10. 2, I'm at 5. And then 5, which is about right here, I'm at 2. And then at 10, I'm out at 1. I keep forgetting that I'm going by 2's, but all right, so that looks okay. Now, I guess if I were to kind of notice trends, as I go down from 0, so like 1, 2, 5, 10 as my x values, I notice that 10 over x is going to get smaller because x is getting larger and it's 10 divided by x. So these values just kind of keep getting smaller and smaller and smaller, and they'll continue to get smaller and it will approach 0. Actually, we have ways to describe that. So that would be the limit as x approaches infinity of 10 divided by x, and that actually is a pretty familiar one because it's just a number divided by something that gets incredibly large, that's going to approach 0. So that is what we actually call a horizontal asymptote. So as you go out towards infinity, it is approaching a finite value of 0. So there is a horizontal asymptote at y is equal to 0. Out the other way, it's going to be very similar. Now, I only did two numbers on the negative side, so I had negative 10 and negative 5, but you can see by kind of symmetry that we would also, if we were to place negative 5 in there, you get a negative 2, and a negative 10 in there, you get a negative 1. So kind of go like this. Now, I didn't do as nice of a job of it that way because I didn't have a graph, but it had that sort of shape to it. All right, now, the question is, and I extended this with an arrow without really thinking about it because we haven't talked about it yet, what's going on in these particular spots? So I can't put in a 0. So what am I really asking? Well, I'm saying, what is the limit as we approach 0 from the right of 10 divided by x, and what is the limit as we approach 0 from the left of 10 divided by x? Those are the questions that I'm really asking here. So if we were to pretend, I like to do it mentally. You can do it with a calculator, and that's fine too. But I'm taking a very, very, very small positive value for the first one because I'm coming in from the right. So a normal number like 10 divided by an extremely small but positive value. Positive divided by positive is a positive. And so we're going to get very large values that are positive. So I'm going to just say positive infinity is what that's going to tend towards. Coming in from the left-hand side, those are going to be negative values. So I'm going to have positive 10 divided by a negative very small number. It's going to give me negative infinity, which from our picture kind of makes sense. So this is just going to extend down forever towards negative infinity. This is going to extend up forever towards positive infinity. And this infinite behavior around a finite value in the middle of the domain also causes asymptotes. So this is a vertical asymptote at x is equal to 0. So we actually have a horizontal asymptote, like we said earlier, at y is equal to 0. And we have this vertical asymptote at x is equal to 0. Great. Other than that, there's not a whole lot kind of going on with this function. If I go back to what the textbook was asking in this particular question, identify characteristics of the graph, including the behavior of the function for its non-permissible value. So what it's asking us to do is just kind of note that, hey, there's some asymptotes here. So we got those characteristics. There are no intercepts. So if we tried to show that, I guess, whoops, sorry about that. So we would have 10 divided by x is equal to 0. 10 divided by nothing gives us, there's no value for x that will allow that to happen. I guess you could say that's kind of the limit idea, but that's not an actual value saying it's infinite. Yeah, so it's, if you multiply the x up on the other side, it just gives you nonsense. 10 equals 0, and so there's no solution to that. So there are no x-intercepts when the y is 0, and then if we test it out, what's the y-intercept? Well, again, 10 divided by 0, that just, again, doesn't make much sense. So neither one of those are going to give us any intercepts, which we saw from the graph. It looked like that was going to be the case. So behavior of the function for its non-permissible value, well, that was a vertical asymptote, and we showed what the behavior was like coming in from the left and the right. So in terms of domain, this thing would have a domain where it was x is not allowed to be equal to 0, but other than that, all real numbers seem to be fine. And then for the range, we have a horizontal asymptote at 0, and there was no crossing it anywhere else along this function. So it tends to just not be able to become 0, which we also showed when we wrote down this little thing about when is the y value equal to 0, and there was no place where that happened. But other than that, we are allowed to, we go up towards positive infinity and negative infinity, and it approaches 0, so 0 is really the only number that's missing there. So those would be like the domain and range for that particular one. So that's just kind of an intro. Use a table of values, see what the behavior's like. Good to go. This is a transformation. So if we go back to Precal A and we think about this form here. So g of x is equal to a f onto b onto x minus h plus k. That's a transformational form, general transformational form of functions that have the vertical stretch or reflections in the a value, the horizontal stretch and or reflections in the b value, horizontal translation in the h value, and vertical translation in the k value. So those four things together kind of give us the full kit and caboodle of things that we know or understand and are comfortable with doing transformationally. So I currently, on this one that's down there right now, have y is equal to 6 over x minus 2 minus 3. If I said that an original function was just 1 over x, how could we turn that into what we currently have? Well, first of all, the argument, the whole thing that goes into where x is, I don't want it to be an x. I want it to be an x minus 2. So that's the same thing as saying I want to evaluate the function at x minus 2 instead. And then I also, I want there to be a multiply by 6 that's occurring here as well. So I want this function to be multiplied by 6. So I'll multiply by 6 by putting a 6 on the front there. And then after that's done, I also want to subtract 3 away from this function, which is a minus 3 here. So you might not be used to rational functions, but we should be able to read off this particular statement and feel pretty comfortable about it. So that's a vertical stretch of 6. It's moved 2 units to the right, and it's moved 3 units down. And those transformations are what allow us to get this new function right here. So g of x, I guess you could say, which is our y in this case, is equal to 6 times this very plain function. That's the 1 over x function. Now, we just graphed 10 over x, so it's not quite the same thing. But 1 over x is a very similar looking function because there's just a vertical stretch that's the difference between them. So when we did 1 over x when we were talking about reciprocal functions. So in this case, it's just your nice base reciprocal function that looks like this. Just going to do a really lazy sketch of it. And then it's going to get stretched, so it's going to be taller, or go up faster, I guess you could say. And so it's going to look something like this instead. And then it's going to be shifted 2 units to the right. This is going to get real messy. So if this was 2 units over, the vertical asymptote would now be moved over 2 units to the right from the 0 position that it used to be at. So it'd be more like this. And then the whole thing is also shifted 3 units down. So it'd be like this. So again, just a really lazy sketch, but it should look something like that. And we can use transformations in order to understand what it should look like. But we can also use our knowledge of mapping notation in order to be able to translate some important pieces of information from one graph to another. So in this case, the mapping notation, or maybe not in this case, so let's say generally. So that's going to be x comma y. Oh, it's been a long time. So this is 1 over b x plus h ay plus k. So it would be our mapping notation generally for this. And so we, if we look at this, we don't have a b value. So our x comma y for this particular case is going to map onto x, and then the h value is 2. So it's x plus 2. And then a is 6. So 6y minus 3, moving it 3 units down. So that would be our mapping notation here. And so if we said that the original function 1 over x, it has some important points because there are, for an original x function, which was, or sorry, y equals x function, which was this thing, we said that 1 and -1 were invariant points under the reciprocal transformation. So that would mean that we have, I'm going to do it in highlighter here, but 1 comma 1 as well as -1 comma -1 as being points that we can transform here. And we can also think about moving asymptotes. So asymptotes are lines that aren't a part of the function, but there are features that bound the function, and because of that, they move with the rest of the transformations. So if we think, for instance, about our vertical dotted line, that is our vertical asymptote at 0, if we were to stretch that, it's already infinitely long. So stretching it doesn't do anything this way. It's sitting at x is equal to 0. So doing something like stretching it this way, it's already 0 units away from the y-axis, so that does nothing too. Moving it up or down, since it's infinitely long, also does nothing. So the only thing that we can really do for the vertical asymptote is to move the vertical asymptote left or right. So the only transformation that moves things left or right is the h part of that transformational form. And so we are moving this thing 2 units to the right, which means the vertical asymptote would also move 2 units to the right. So that would be at x is equal to 2 instead of x is equal to 0. Again, we could do the same thing with the horizontal asymptote. So our horizontal asymptote is at y is equal to 0. If we stretch it this way, it doesn't matter because it's infinitely long to begin with. If we move this thing left or right, or well, I know it's opposite to you, so I got to think here. So this is left or right, then you should have nothing happen to it because it's infinitely long. Just basically moves this thing that you can't tell that it's moving because it's so long. And then if you were to stretch it this way, it's 0 units away from the x-axis, so it doesn't stretch at all. And so our only option really is to move it, so we can move it vertically up or down. So the part of our function that moves things up or down in transformational form is the k. The k value here is -3, which means that our horizontal asymptote is going to occur at y is equal to -3. So we could do what I did up here and basically just like move the whole thing around visually. We can think about the transformations without having a graph involved at all, really, and be able to move your asymptotes, and then maybe get a couple important points. So if we have the 1, 1 point, and we were trying to describe where that's going to go, according to my transformational form up here, I would take 1 plus 2 is 3, and 6 times 1 is 6 minus 3 is 3. So I would have an asymptote, no, sorry, not an asymptote, a new point at the 3, 3 location. Now, I am also going to have a -1 point, and this is going to map onto -1 plus 2 is 1, and then -1 times 6 is -6 minus 3 is -9. So I would be able to place those down and get an idea of where that would go. So I'm just going to do a really lazy sketch. So if this was x was equal to 2, and this was y is equal to -3, and then at the 1 point, I'm down at -9, which is somewhere way down here. And then at the 3 point, I'm going to be up at +3, which is somewhere around there. So again, I'd have something kind of, other than that, it has the same shape because we've just moved and stretched potentially it around, so it looks something like that. Now, of course, that's, I could put it up against a little graph, but that was probably one of the poorer sketches that I've done. So let's just say we have f of x, and we are going to say that that's 6 over x minus 2 and -3. So just as a kind of a general shape, things look good. If I wanted to give some sort of borders or boundaries to what's going on, we might say that this is at x is equal to, and we actually stated it was going to be 2. So we think that this should have an asymptote at x is equal to 2, and then it should have an asymptote at, horizontal asymptote at y is equal to -3. If I take those and just kind of make them so that they're obviously not the function itself, so it would look like that. Projector mode a little bit easier to see. So that looks good. Those asymptotes look like they are definitely describing the end behavior on that side. That looks pretty nice on that side too. It just kind of gets really close without ever crossing it. And then this infinite behavior that's happening because of the limit as we approach, it would be approaching now +2 from the left and the right instead of 0 from the left or the right. But if we think about it transformationally, it was the original 1 over x function, its behavior. Okay, because this is opposite of what I think, so I'm going to have to, oh gosh, this is awful, like this. Is that, yeah, that is right. Anyway, I'm never going to get used to that. Like that being said, when you're teaching in front of a class, it's the same. So it's backwards, because you would see from this side, so this would be your quadrant 1 anyway. So I guess I should get used to that, right? I suppose I could just write it down and that works out as well. All right, so this is just being able to identify some of the interesting things about this. Now, one of the other things, though, that we may wish to do is be asked about asymptotes. Now, one of the things that I did was I just moved things around, and I didn't give you any clear indication on this absolute mess of a picture of where this thing might cut through the x and the y-axis, but it definitely looks like it does both. If we look at the graph of here, it definitely looks like it does both as well. So how would we find those positions if we were interested in them? Well, our original function is this. And so if that's what we have, and we said, let's set our y equal to 0 and see what happens. So I'll move my 3 over to the other side, and I'll multiply my x minus 2 up. So I get 3x minus 6 is equal to 6. So 3x is equal to 12, which means x is equal to 4. So we have a single x-intercept, because it was a linear function that we solved, that occurs at x is equal to 4. If I just double check that, not that that's necessarily going to be the case for these ones, but it's always good to make sure that your values that you get are actually a part of the domain. In this case they are, because it's only positive 2 that would be not a part of the domain. So x is equal to 4, great. So that's 4 comma 0, because this is an x-intercept. And then if I do the same thing, so I guess I probably should just start over again. So 6 over x minus 2 minus 3. And this time I'm going to say that the x value is 0. So I get 0 minus 2 minus 3. So y is equal to 6 divided by negative 2 is negative 3. Minus another 3 is negative 6. So that would be at 0 comma negative 6. We should have a y-intercept. So this is our y-intercept. Oops. And this one up here is our x-intercept. So let's just double check and see how Desmos feels about those particular values. So if I come along here and we take a look at this value, that is definitely at 0, negative 6. So that y-intercept is good. And this one over here is at 4 comma 0, so that x-intercept was also very good. And so we can solve algebraically for intercepts, and we should always come across ones that end up solving nicely at this point. But just set your x or y equal to 0 and solve to see if you can find nice intercept values. So we've been able to describe your asymptotes. We've been able to describe the location of intercepts. Intercepts are a little bit awkward because you can't, it's not that the old intercept becomes the new intercept. So if we followed an old intercept, there were no old intercepts on the 1 over x function. So they become intercepts when you've shifted this thing around. You have some ones that now exist, but you can't just follow along old ones and assume that they become new ones. So we have to solve them algebraically. We can't just use mapping notation and hope that we're going to luck into it. I mean, you could, but you're probably going to be fiddling around for quite a bit before you find something. So there, that's finding something that's already written nicely in a transformational form, being able to describe that versus the 1 over x function. All right, so this is where it's going to start differing from the rational functions. So this is a little bit different. So this one says graph a rational function with linear expressions in the numerator and denominator. So identify any asymptotes and intercepts. The problem with this one is it's not really a straight up transformation. So it's kind of a little bit odd that it's in 9.1, the way that the section is titled. But that's okay. It's a good thing to think about anyway. So part of this is going to be done transformationally. So normally dividing by x causes an oopsie-doo to occur at x is equal to 0. So then we're going to have a vertical asymptote. This thing has had its asymptote shifted over to positive 2. So we can take a look at this x minus 2 and basically just think, what number would cause this denominator to misbehave? So if we, oh, I forgot. I'm sorry about that, folks. So I'll switch over here. I'm going to be lazy. I'm not going to splice it all together because it takes a long time. So this is the question that I'm supposed to be looking at with you. 4x minus 5 divided by x minus 2. Identify any asymptotes and intercepts. So as I said, it's kind of a little bit odd because it's not really done in a transformational way, but that's okay. So first of all, asymptotes. What we're really saying is, what is the limit as x approaches 2 from the right, and what is the limit as x approaches 2 from the left of this thing? So we know that there's going to be it's going to give us problems, because if we put it in 2, we can see that the denominator becomes 0. If we approach 2 from the right, that's going to be numbers like just a little bit bigger than 2. So 4 times something a little bit bigger than 2 minus 5 is positive up top, and down bottom it's going to be a little bitty positive number. So positive divided by positive gives us positive infinity. And then for the other one, I'm going to have things like 1.99999. So still going to be positive up top. It's going to be pretty close to 3 positive. And then down bottom, I am going to have a negative that is divided by. So because of that, this is going to approach negative infinity. So I have this idea already that if I were to, again, just quickly and lazily sketch this, and this was to be at x is equal to 2, that I know on the right-hand side, I am up towards positive infinity, and on the left-hand side, I'm towards negative infinity. And the way I know that is, coming in from the right, we tested it as being positive infinity. Coming in from the left, tested as being negative infinity. This is the left side of it, negative infinity. Right side of it, positive infinity. So those are just kind of gives me some how this is going to look a little bit. All right. Now, something else that's interesting, though, is that we want to know end behavior as well. So the end behavior is what's going to tell you how this function behaves out towards positive infinity and negative infinity. Now, this is going to be interesting because we just did a bunch of these in our limits section, so they should look very, very familiar. Highest power of x in the numerator and denominator is 1. So the rule is, if it's the same in numerator and denominator, you take the ratio of the coefficients. It's 4 divided by 1 gives you 4. Whether you put it in positive or negative infinity doesn't matter in this case, because it would be negative divided by negative. So you're going to get a positive 4 in both cases, which means that this thing, I'm not scaling it right, but that's okay, would be at y is equal to 4. Or not that it's wrong, it's just I have a different scaling on my x and y axis. I couldn't move the other one over, but I didn't give myself enough room otherwise. All right, so we'll leave it at that. And so I get my horizontal asymptote at y is equal to 4 because of the limit work that we did there. So I have, you can almost see what's going to happen, because this is going to come down along this horizontal asymptote, and it's just going to go along there. This one's going to come up, and it's going to go along here. So we expect there to be some sort of y-intercept likely and x-intercept, because in order for it to follow along positive 4 as it goes out towards negative infinity, it's going to have to cut through both the x and the y-intercepts. So if we cut through that, let's figure this out, I guess. Y is equal to 4x minus 5 over x minus 2. If we were looking for the x-intercepts, that's when your y is equal to 0. And so really, if we kind of come up with a way to talk about that quickly, that is always going to mean when your numerator is equal to 0, because the denominator doesn't make the division equal to 0 ever, not with a real number. So as long as the answer to this, which is 5/4, does not disagree or does not give you something that is outside of the domain. So in this case, the domain issue is at 2. This is 5/4. That's fine. So we're going to see that there is at 5/4, which again I sketched it in a kind of a weird way. But that would be 5/4 is a little bit beyond 1. It looks like I'd put it kind of at 1, but that's okay. And so that would be our x-intercept. Our y-intercept is going to be done basically the same way, except for we're going to put in that the x value is 0. And so y is equal to -5 divided by -2 is equal to 2.5. So we would see here that this should occur at 2.5. And so if I were to graph this thing, we would have, well, if I did by hand and I did it nicely, after having found the intercepts, we'd have the intercepts appropriately found. We'd have the horizontal and vertical asymptotes in the right spots. So we should be able to make a fairly nice picture of this thing. And so if I were to, oops, I guess I want this one. Yeah. If I were to graph it, see how we did. This would be 4x minus 5 divided by x minus 2. And so, I mean, kind of looks similar here and here. However, let's just make sure. So we had said that we were going to have a horizontal asymptote. Oops, y is equal to 4. That's my fault. Y is equal to 4. That looks pretty good. And again, I could dot it and things, but well, that's good for the time being. And it was going to be at x is equal to 2 for this one. So that looks good too. Those colors are awful because it's the same as the original. I guess I should have dotted them too or dashed them. All right, so that looks excellent. And then we also found that there was an intercept at 0, 2.5 for the y. Bam, that looks great. And then we said 5/4 for the x-intercept. So 5/4, 0, and nice. All right, so both of those look perfect. So we did a good job of graphing this thing by solving its intercepts and understanding where its asymptotes would be by looking at them as limits. So limits as you approach interior numbers that are wonky because you're dividing by 0, or limits because you're going out towards the ends and you're assessing what's going on at either negative infinity or positive infinity. All right. Yeah, I think I'll take a quick look at this and just kind of discuss some quick differences between these functions. So the g function, oh, I did it again. There we go. All right, so the quick differences between these three functions. F of x is equal to 1 over x squared, g of x is equal to 3 divided by x squared minus 10x plus 25, and h is equal to 6 minus 1 over x plus 4 all squared. So we should be able to kind of say some interesting things about these pretty quickly. The 1 over x squared function is going to look pretty similar to the 1 over x function, except for it can never be negative because you're going to take the square root of it. So your 1 over x function looks like this. So your 1 over x function is going to kind of look like this. Now, technically, the square is going to make it curve a little different. So it's going to be a little steeper in some spots, and it's going to be more shallow out towards the outsides because you approach the lower values faster and you kind of stay flat. And then it kind of spikes up in the middle faster because of the square. But it has a lot of the same general shape, just no negative values. So if you wanted to assess this by saying what's the limit as you approach x from the right of 1 over x squared, and what is the limit as you approach x from the left, 0 from the left of 1 over x squared, then you could kind of use those test values, use like 0.0001 and negative 0.0001, and see that because it's squared, doesn't matter whether it was negative or positive, you get those really, really large positive values, so they both shoot up towards positive infinity. So that's kind of what that one's going to look like, just really briefly. The other two can be seen as transformations of that original function. So the g of x function in particular doesn't really look like it the way that it's laid out, but that bottom is actually a perfect square. So x squared minus 10x plus 25 would be x minus 5 all squared. So another way to write that would be 3 divided by x minus 5 all squared. So transformationally, this is a shift of 5 units to the right and then a vertical stretch of 3 units over the original function. So it's going to have a lot of similarities, I guess. And then for h, I probably, as funny as it is, I'm going to, just for the ordering sake, I'm going to write the second term first, the fraction part, and then I'm going to say plus 6 like that, because it's in the same order as we would normally see transformationally if I do that. So this is a vertical flip, and then you're going to shift this thing 4 units to the left and 6 units up. So if I were to just say, well, what's the difference between these things? Well, my original kind of looks like, wow, I'm really sloppy, like that and that. And then my other one, I'm going to shift 5 units to the right, and it's going to grow faster. So 1, 2, 3, 4, 5, I don't know, like, I'll just put it over here. And then it's going to grow even faster. And then I have my other one is going to flip upside down. It's going to move 4 units to the left, and then it's going to move 6 units in the air. So it's going to be upside down, so it kind of looks like this instead. But then I move it to the right, which is going to be over here some, but then I move it up. So it's going to be, in the end, kind of somewhere up there. Let's see if I can properly remove the rest of that stuff. So it's going to look kind of like that. So I'm just going to do a quick graphing of these 3 things in Desmos to just see if we understood the general idea of what these look like and how they would look with these transformations. Again, we could do a much better job by finding intercepts and asymptotes and carefully maybe taking a couple points and doing mapping notation. But let's just see if we have a feel for how these things behave. So this is going to be 1 over x squared. So that's the one we just kind of talked our way through and said it was going to be a lot like 1 over x, but it would be steeper and positive on both sides. So the other one is going to be 1 over x. So 1 over x squared minus 10x plus 25. So because I just flipped that over. That red one's our 1 over x squared. This one over here is our second one, which was the g of x function. And then the last one is going to be 6. I'll write it the way that it's written, even though we switched it, or I switched it when we did it together there. X plus 4, and then all squared. So that looks actually pretty reasonable. So I'm going to put it up against what I had on my, my iPad, so I'll switch spots there. So down there is Desmos, and so we have this like funky blue one that I did a really lazy job of. It looks like this black one. And then this one definitely is the red one there, and the one over to the side there, the purple one, is this one over here. So looks like we kind of, or if you followed along with my arguments there, have a way to associate those and get them so that we understand the characteristics and how they're related to each other by looking at transformations. So what I'm going to do is I'm probably going to end it there, and I'll post some things from the textbook that you can take a little bit of a look at. And hopefully you're doing well. If you have, if you're going to make a trip to the school this week and it's Thursday, maybe I'll see you there. That's my day to do a little bit of supervision. And if not, stay safe and thinking of you. Take care.